Good morning, students. After the completion of the chapter noble gas element, that is a group 18 element, next we go to next chapter, that is group 17 elements or halogen family. Mark that. Next chapter is group 17 elements or otherwise known as halogen family. In this chapter, today the first class, I will try to complete the introduction part, nomenclature of this family, then general trends in periodic property, that is physical property, general trends in chemical property, then anomalous behavior of chlorine, next general method of preparation, property and uses of halogen compound, that is chlorine. So let us start one by one. First one is introduction. First one is introduction. That means there are 5 elements are there known as chlorine, bromine, iodine and astatine. I repeat again. The elements chlorine, bromine, iodine and astatine constitute a family, that is group 17 or VIIA of the in the periodic table. I repeat again. Chlorine, bromine, iodine and astatine, that is very much reactive nonmetals, constitute a family known as group 17. They are also known as halogens, which mean sea salt. That means maximum of them are available in the form of salt in seawater. That's why they are otherwise also known as halogens. All of them are very much non-reactive element, very much reactive nonmetals. That's why they are not available in nature freely. All of them, maximum of them are available in the form of salt in seawater. Next we discuss about the electronic configuration. Next, electronic configuration. From the normal electronic configuration, it is clear that all of them possess similar electronic configuration. All of them possess 7 electrons in their valence shell, having a common outermost electronic configuration is NS2 NP5. Mark that from the box diagram, that is elements, atomic number, noble gas, electronic configuration. First one is chlorine, bromine, iodine, astatine. The atomic number 9, 17, 35, 53, 85. If we go through the noble gas configuration, it is helium 2, 2s2, 2p5. Next, neon 10, 3s2, 3p5. Next, argon 18, 3d10, 4s2, 4p5. Then krypton 36, 4d10, 5s2, 5p5. Last one xenon 54, 4f14, 5d10, 6s2, 6p5. Mark that. From this electronic configuration, it is clear that the valency cell, that is 2s2, 2p5, 3s2, 3p5, 4s2, 4p5, 5s2, 5p5, 6s2, 6p5. That means the common possess ns2, np5. That means from this electronic configuration, it is clear that all of them have a tendency to accept one electron in order to obtain the noble gas configuration. So they have a strong tendency to accept an additional electron to possess the nearest noble gas configuration. That's why they are very much reactive nonmetals. And all of them possess ns2 and np5 electronic configuration. As the last electron enter to p subcell, that's why they are also belongs to p block of the periodic table. In the previous class already we discussed, that is the total periodic table divided into 4 block, that is s block, p block, d block and f block, depending upon the entrance of the last electron, the valence electron in the respective subcell. Next, we discuss about general trends in physical properties. Next, we discuss general trends in physical properties. Under this heading, I will try to discuss the following points. That is, point 1, atomic and ionic radii. Next, ionization energy. Next, electron affinity. Next, oxidation state. Next, bond dissociation energy. Mark that. Under the heading of general trends in physical property, now I discuss the following points. I repeat again. Atomic and ionic radii, ionization energy, electron affinity, oxidation state, and last one is bond dissociation energy. Let us discuss one by one. First one is atomic and ionic radii. If we look after the atomic radii of this family, halogen family, then we conclude that they possess lowest atomic radii in a respective period. Because we know that a common concept, the atomic radii gradually decreases across a period, while atomic radii gradually increases in a group from top to bottom. I repeat again. Atomic radii gradually decreases across a period due to increase in nuclear charge. That's why in each respective period, atomic radii gradually decreases up to the 17 element group, 17 element, that is chlorine, bromine, iodine and aspartate. So they have lowest value of atomic radii in respective period. Next, that is ionization energy. Next point, ionization energy. What is ionization energy? What do you mean by ionization energy? It is defined as the amount of energy required to remove the valence electron of a neutral gaseous atom in order to form a monovalent positive ion or a cation. I repeat again. Ionization energy is defined as the amount of energy required to remove the valence electron of a neutral gaseous atom in order to form a monovalent positive ion or cation. So due to their small atomic size, they have high value of ionization energy. However, if we move from chlorine, bromine, iodine to astatine, there is fluorine to astatine, from top to bottom in the periodic table, this value gradually decreases due to increase in atomic size. Next is electron affinity. What do you mean by electron affinity? It is defined as the amount of energy released. It is defined as the amount of energy released when an extra electron is added to a neutral gaseous atom in order to form a monovalent negative ion or anion. In other words, electron affinity is defined as the tendency of an atom to attract the electron from another atom. So from the normal electronic configuration, that is NH2, outermost electronic configuration, NH2, NP5. So from this electronic configuration, it is clear that they have a strong tendency to accept an additional electron in order to maintain the nearest noble gas configuration. That's why they have high value of electron affinity. However, while moving from top to bottom, this value gradually decreases as atomic size increases. Next point is oxidation state. From the electronic configuration, it is clear that they possess a common valence electronic configuration, that is NH2NP5. That's why they have a strong tendency to accept or share one electron to form noble gas configuration. I repeat again. From the electronic configuration, it is clear that all the members of this family possess a strong tendency to accept or share one electron to acquire the nearest noble gas configuration. So, they exhibit a common oxidation state of a -1 or a +1, depending upon the other element with which combine possess lower electronegativity or higher electronegativity. I repeat again. They exhibit a common oxidation state of a -1 or a +1 depending upon the element with which they combine. That one possesses lower electronegativity or higher electronegativity. Fluorine possesses only one oxidation state. From the electronic configuration, it is clear that due to its small size and among the family highest electron affinity, and also non-availability of vacant d orbital, it exhibits only one oxidation state, that is a -1. I repeat again. due to small in size, higher electron affinity, and a non-availability of vacant d orbital. Excitation of electron is not possible. That's why fluorine exhibit only one oxidation state, that is -1. However, while moving down the group, other member of this family possess, as they have electron affinity decreases, as they have presence of vacant d orbital, so excitation of electron takes place. That means excitation of electron of d orbital, then p orbital and s orbital takes place, having the more than variable oxidation state. In addition to -1, they also exhibit +1, +3, +5, and also +7 in addition to -1, because of lower electron affinity and also presence of a vacant d orbital. Excitation of electron takes place. Let us verify in the form of a box-like diagram. Mark that. They have a common, that is NH2 NP5. Ground state electronic configuration. It is NS, NP, ND, NH2, NP5. That is, it is the electronic configuration of halogen family other than fluorine. That is, it is applicable for chlorine, bromine, iodine, astatine, where there is a presence of d orbital. Mark that. So from this it is clear that since only one paired electron is there, so it can accept one electron or share one electron, showing an oxidation state of -1 or +1. So in this case, oxidation state is equal to -1 or +1, depending upon the element with which combine possess whether lower electronegativity or higher electronegativity. Next, the first excited state. On excitation, it is first excited state electronic configuration. Mark that. So from this electronic configuration, it is clear that they possess 3 unpaired electrons. Since these are applicable for other halogen except fluorine, so they possess lower electronegativity. That means they have the tendency to lose electron. That means from this electronic configuration, it is clear that they exhibit a common oxidation state of +3. Move to next one. Second excited state electronic configuration, that is second excited state electronic configuration. Mark that. Mark that. From this box-like diagram, it is clear that they have a 5 unpaired electron. So as they have lower electronegativity, they are able to share the 5 unpaired electron, showing a common oxidation state of +5. So here oxidation state is equal to +5. Next, third excited state. Next one is third excited state electronic configuration. Mark the box like diagram. Mark that. From this box like diagram, it is clear that except for in other halogens, in case 7 unpaired electrons are there, as they have lower electronegativity, they have the tendency to donate the 7 unpaired electron, so showing a oxidation state of +7. So here oxidation state is equal to +7. That's why due to the absence of vacant d orbital, excitation is not possible in case of chlorine. That's why positive oxidation state is not shown. In addition to it, chlorine possesses highest electronegativity. That's why excitation is not possible. And also the absence of vacant d orbital. On combining this one, chlorine exhibit only one oxidation state, that is a -1. But besides chlorine, in other cases, due to the lower electronegativity and presence of a vacant d orbital, excitation of electron not only from the d subcell, it also takes place from p subcell and s subcell, as a result of which, in addition to the -1 oxidation state, they exhibit a variable oxidation state, positive oxidation state of a +1, +3, +5 and a +7. Next we go to another point, that is bond dissociation energy. Next is bond dissociation energy. From the electronic configuration, it is clear that due to its small atomic size, higher electronegativity, due to its higher affinity, and non-availability of vacant d orbital, chlorine possesses low bond dissociation energy because of repulsion between non-bonding electron present in the 2p orbital. I repeat again, due to its small atomic size and absence of vacant d orbital, there is the inter-electronic repulsion present the unpaired electron in the 2p orbital. That's why the bond dissociation energy of a fluorine is low. But in other cases, due to the presence of vacant d orbital, so multiple overlapping in the d orbital takes place. That's why other member of the family possess higher bond dissociation energy. It is all about general trends in physical property. Next, switch over to general trends in chemical property. General trends in chemical properties. Under this heading, I will discuss reactivity, next affinity towards hydrogen, next affinity towards oxygen. Under the heading of reactivity, I will discuss 3 points mainly: reactivity, affinity towards hydrogen, and affinity towards oxygen. Let us discuss one by one. First one is reactivity. Among the halogen, fluorine possesses highest reactivity. Among the halogen, fluorine possesses highest reactivity due to the following points. What are the points? Point 1, low atomic size, low bond dissociation energy, high electronegativity, and high oxidizing power. I repeat again, the following points are, that is, fluorine possesses highest reactivity among the halogen due to, point 1, small atomic size, less bond dissociation energy, third, high electronegativity, and fourth one, high oxidizing nature. I repeat again. Among the halogen, fluorine possesses highest reactivity due to small in atomic size, less bond dissociation energy, high electronegativity, and high oxidizing nature. However, the reactivity gradually decreases on moving down the group, because in other cases, due to the presence of a vacant orbital, excess excitation takes place, as a result of which multiple overlapping takes place, that is high bond dissociation energy. As a result, reactivity gradually decreases. Next, we discuss affinity towards hydrogen for the formation of halo acid. Next is next chemical property, affinity towards hydrogen. The halogens combines with hydrogen to form halo acid. I repeat again. Halogens combine with hydrogen to form halo acid, that is represented by the formula HX, that means HF, HCl, HBr, HI. These are known as halo acid. Normally, in a dry state, they are not able to behave as acidic nature. They exist acid, they behave acidic nature in presence of moisture or water solution. So under the heading of affinity for hydrogen, that is towards the behavior of halo acid, let us discuss some points. That is degree of volatility, degree of polarity, degree of thermal stability, oxidizing nature, reducing nature, last one is acidic nature. These are some points relating to the behavior of acid. We know that they are covalent in nature, and the degree of volatility HF in first one is hydrochloric acid or hydrogen fluoride. Due to the presence of intermolecular hydrogen bonding, bond strength is higher, so degree of volatility is low. So the order of degree of volatility is HCl, HBr, HI and HF. And they are covalent in nature, and we possess among the halogen, that is highest electronegativity fluorine, then this value decreases. So if we discuss about the degree of polarity, then it becomes HF decreases as HCl, HBr and HI. Due to the magnitude of van der Waals force, and also there is the hydrogen bonding, HF is the strong one. So the thermal stability decreases, also HF, HCl, HBr and HI. Next, oxidizing nature. This value also decreases as HF, HCl, HBr, HI. Oxidizing nature. What do you mean by oxidizing nature? That is, oxidizing agent helps in oxidation. Oxidation means loss of electron. That species which helps in losing electron means itself gain electron. So highest tendency of fluorine due to the highest electronegativity. So this value gradually decreases. Next is reducing nature. As we know, reducing nature is the reverse of oxidizing nature. So this value gradually increases as this one. Last one is acidic in nature. In dry state they are not behave as acid. In moisture, in aqueous solution they behave as acid. And due to the presence of intermolecular hydrogen bonding, bond strength is higher, and as a result of which degree of dissociation, ionization difficult. So acidic nature increases as HF, HCl, HBr, HI. These are some characteristic property relating to the halo acid. Next chemical property, affinity for oxygen. Next chemical property, affinity towards oxygen. All the halogens, due to their small atomic size and higher electronegativity, they also combine with oxygen to form halogen oxygen compound. And if we discuss about fluorine, due to small in size and higher electronegativity, when fluorine combines with oxygen, that compound is known as chlorides of oxygen, but not oxides of fluorine. I repeat again. When fluorine combines with oxygen, resulting in the formation of compounds known as chlorides of oxygen, but not oxides of fluorine. But in other cases, in case of chlorine, bromine, iodine, due to their lower electronegativity in comparison to oxygen, when they combine with oxygen, they are known as oxides of halogen. I'll repeat again. In case of other halogens, when they combine with oxygen, the compound form known as oxides of halogen. But in case of chlorine, the compound is known as chlorides of oxygen, but not oxides of chlorine. Next we discuss anomalous behavior of chlorine, abnormal behavior of chlorine, peculiar behavior of chlorine. Next we discuss anomalous behavior of chlorine. There are two mark question. Question 1. What is the reason behind which chlorine behaves differently from other member of this family? Question number 2. What are the different behavior of chlorine? Two mark question. I repeat again. First question is, why chlorine behaves differently from other member of the family? Point 2. What are the different behavior of chlorine? So we discuss one by one. Bit 1. The anomalous behavior, abnormal behavior, something different behavior of chlorine due to the following points. That is, point 1, due to small in atomic size. Point 2, absence of a vacant d orbital. Next, low bond dissociation energy. And the last one, high oxidizing nature. Due to the following points, chlorine behaves differently from other member of this family. Mark that. Due to small atomic size, absence of vacant d orbital, low bond dissociation energy, high oxidizing nature, and high electronegativity. Next we discuss what are the different behavior of a chlorine. Next, anomalous behavior of chlorine. Some points are there. That is, point 1, exhibit only one oxidation state due to highest electronegativity and absence of vacant d orbital. It possesses only one oxidation state, that is -1, while other possess, in addition to -1, possess variable oxidation state of +1, +3, +5 and +7. That is, exhibit only one oxidation state, that is -1. Point 2, due to small atomic size and absence of a vacant d orbital, so inter-electronic repulsion takes place. That's why they possess low bond dissociation energy. While In other cases, due to the presence of vacant d orbital, multiple overlapping takes place between the electron in d orbital. Multiple bonding takes place in d orbital. So second point is low bond dissociation energy. Third one is highest reactivity. Due to low bond dissociation energy, due to highest electronegativity, fluorine possesses highest reactivity among this family. However, the reactivity gradually decreases. So next point is high reactivity. Next point. The last point, the important point is exhibit maximum covalence. That means due to smaller atomic size, highest ionization and highest electronegativity, and less bond dissociation energy. That means the combining capacity, covalency is maximum, and exhibit, that is combining capacity, is only one. But due to the higher electronegativity, maximum number of fluorine atom combine with the central atom, as a result of which its combining capacity increases. Due to this same reason, SF6 is possible while SH6 is not. That means the last point is maximum covalency. Maximum covalency, that is combining capacity. Due to, I repeat again, due to smaller in atomic size, low bond dissociation energy, maximum number of fluorine atom, combine with the central atom. Due to this reason, I repeat again, due to this reason, SF6 is possible while SH6 is not. Mark that. It is a 2-mark question. What is the type of question? SF6 is possible while SH6 is not explained. Answer. In case of fluorine, due to small in atomic size and highest electronegativity, fluorine able to excite the electron of sulfur, making the unpaired electron up to maximum of 6. So here sulfur exhibits 6, and we know fluorine only one oxidation state, that is -1, resulting in the formation of SF6. On the other hand, no doubt due to small atomic size but not possess a higher electronegativity in comparison to sulfur, as a result of which hydrogen unable to excite the electron, unable to increase the covalency of sulfur. That's why SH6 is not possible. I repeat again, it is a 2-mark question, a reasoning question. Explain SF6 is possible but not SH6 reason. The main concept is that maximum covalency.